Alrighty, my people. I hope we are doing well. This is attempt number 3 at trying to do this video, so I'm hoping that this one actually takes. Um, let's go ahead and try and remember where we were before we left on spring break a little over 2 weeks ago. And we were discussing the fundamental theorem of calculus. And if you remember, there are actually two parts to the fundamental theorem of calculus. Um, and actually, sometimes books call them, FTC Part 1 and FTC Part 2. Some books call them the first fundamental theorem of calculus, and the other one the second fundamental theorem of calculus. And the order, like which one's first and which one's second, is completely arbitrary because some books label them one way and some books label them another way. And in fact, I am disagreeing with Stewart the way that our book designates the order of them, and I am calling this Part 1. I just wanted to let you know that, and that sometimes labels are important and sometimes labels are completely arbitrary. I wanted you to know that so that if you hear somebody else talking about calculus in the future and they're referring to this one as Part 2, you don't argue with them. You realize it's just there's nothing to it. Okay. Now, before we got to the fundamental theorem of calculus, we started a unit where we were dealing with undoing derivatives, right? We were dealing with what is called anti-differentiation, or what are called anti-derivatives, and it was purely a section that was technique based, right? It was not really a whole lot of conceptual richness. We were just trying to get our brains used to going in the opposite direction from what we were doing, right? Instead of x cubed becoming 3x squared becomes x cubed. And so we basically went through some practice problems in 4.9 simply to get us in the habit of being able to go in that other direction. And we didn't yet call it an integral. We called it antiderivatives, and instead of going from f to f prime, we went from f to big F, right? And that was just the way that we labeled it. And of course, it's a little bit arbitrary, but it basically got us to practice that undoing of derivatives without being distracted by new notation as well. In 5.1 and 5.2, that's where the concept comes in. And we talked about area under the curve and approximating area under the curve and sums and ultimately what are called Riemann sums. And basically we introduced limits to it for the same reason that we introduced limits to finding the derivative by means of taking a secant line and transforming it into a tangent line. Right? And basically this was the conceptual backdrop of ultimately integration that we're going to be dealing with. Okay? And I basically told you that just like derivatives are not slope, right? Slope is one way that a derivative, or what is a rate of change, can be pictured or described, but that doesn't make derivatives slope, right? In the same way that we enter into our understanding of integration by means of area under the curve, that doesn't mean that the integral is area under a curve. In fact, I was very careful to divest you of that misunderstanding. Basically, the integral is a way of accumulating, okay? Now, after we dealt with finding those approximate areas and then running those approximate areas off to infinity by means of the number of cross sections, right? So instead of the area under the curve, instead of the area under a curve from A to B being divided up into 4 cross sections or 8 cross sections, we basically wanted to deal with the infinite number of infinitesimally thin cross sections that had a height of the function value at that input and a width of an almost imperceptible infinitesimal amount, might as well be 0 dx, okay? And that's basically, remember, that's why derivatives and integrals are inverses of each other, right? Here, we are dividing by 0 and not getting undefined. Here, we are multiplying by, functionally, 0 and not getting 0, okay? And it's, of course, the limit. It's the logic of mathematics of approach that allows us to do this. The moment that we step out of mathematics of equality and get to mathematics of approach, that allows us to do these fun things. Now, remember that I basically went through the Riemann sum stuff with you for the same reason we went through the limit definition of the derivative, and that's because each time you do the technique, you need to know what's going on conceptually behind the scenes, and that limit is going on, okay? Now, after we basically did the technique and I introduced the concept, this is 5.3, specifically part 1 of the FTC, is basically the marriage of technique and concept. And we get the sum of the infinite number of cross-sections of height f of x and width dx between a and b. And it's equal to the antiderivative at b minus the antiderivative at a. Okay? Now, Riemann sums are done in terms of sigma notation, sigma for sum. There is a reason why the integration symbol looks like a nice big elongated S, because it is a sum in the same way that a sigma is a sum. It's just a sum of an infinite number of infinitesimally thin cross-sections, and that's why we no longer get an approximate answer when we're looking for area under the curve or whatever your integral stands for. You get an exact answer, okay? Now, let's go ahead, now that we've sort of reviewed the conceptual stuff behind it, let's go ahead and work on a couple of problems to sort of knock the cobwebs out and get ourselves reacquainted with calculus in order to be able to, have more fun with math. So let's try the example, the integral from 1 to 8 of x to the 4/3 dx, okay? Now, if you were to ask me what that function looks like, I could go ahead and put it on the calculator. Let's see if I can get it to a place where there's no glare. And the function looks a little bit like that. Now, if we took the time to stop and reason it out, I could actually explain to you why this is, because the x to the 1/3, right, basically is the inverse of the cubic, and then what happens when you square that and then square it again, okay? But this doesn't actually tell us what we need to know so much, so let's go ahead and change it from 0 to 10, since I'm going from 1 to 8, and let's change the y-min, let's go 0 to, 25. How about that? And we'll even do this one by 5s. And if we redo that, we see the function between 1 and 8, actually on this window between 0 and 10, and that gives us an idea at least how big our answer should be, so that we'll come back to this and determine whether our answer is reasonable. Now remember that when we're dealing with the integral like this, we need to undo the derivative, undo differentiation. So what function is x to the 4/3 the derivative of? Okay. Now remember that this is basically the chain rule, and when we're dealing with the chain rule in terms of differentiation, it's x to the n, and you bring the n down and it becomes x to the n minus 1. Well, when I'm dealing with antiderivatives, and if I'm given x to the n, I don't need to subtract 1 from it, I need to add 1, okay? And I don't need to multiply by the old, I need to divide by the new. Okay, so keep that in mind. If I have x to the 4/3, I need to add 1 to its exponent, and 4/3 plus 1, or 4/3 plus 3/3, is 7/3. Now I need to divide by 7/3, but that's the same thing as multiplying by 3/7. Now, I have done the antiderivative, so the integration symbol needs to go away. But I have not yet plugged in my limits of integration, so I need a way of keeping those around, and that's what this cute little line does, okay? Now what I'm going to do is I'm going to plug in 8. Let's go ahead and factor out the 3/7, right? If I plug in 8, remember when I have a fractional exponent, that's asking me to do two things. This one is asking me to take the cube root and raise it to the 7th power. Now the cube root of 8 is 2, and 2 to the 7th power is 128. Now when I plug in 1, it doesn't matter, it's just 1, right? And this winds up being 3/7 times 127, or 381 over 7. Now, that winds up being about 54.429, okay? And if you think about the graph, that actually looks like a reasonable number for that sum, okay? And just imagine just an infinite number of infinitesimally thin cross sections being added up between 1 and 8 underneath that curve. Now let's go ahead and look at one that's a little bit different, but in a lot of ways remarkably the same. Now this one is not quite as straightforward as the one that we just saw. That one was basically power rule, just waiting for us to go through with it. This one actually is also the power rule, but it requires a bit of simplification before I get going, okay? Now just because 2 over x is altogether underneath the radical does not mean that it needs to remain that way, okay? Remember, when we're simplifying, we need to ask ourselves, can we take this apart? Now, if it had been given to you like this, perhaps you would have seen that you can, remember, this is a limit, so I can take that constant and pull it out in front, and this winds up being that right there, right? Because the x is being square rooted in the denominator, okay? X to the negative 1/2, after I pull that root 2 out in front. Now from here it winds up being extremely easy, okay? Just like the last one, I'm going to add 1 to the exponent, and then I'm going to divide by the new exponent, which is 1/2, which is the same as multiplying by 2. Now I've done my anti-differentiation, so I get rid of the integral symbol, but I need, again, to remember that I'm plugging in those limits of integration. And if I have, let's go ahead and pull the 2 root 2 out and just apply the 8 and the 1 to the x to the 1/2. When I take the square root of 8, it is also 2 root 2. And when I take the square root of 1, it is 2. Now, of course, you can sort of unsimplify if that helps you, okay, and call it that, because that might actually be a little bit easier. Or just remember that when you distribute this to the first one, it's root 8 times root 8, which of course just gives you 8. And when you distribute it to the second piece, it's going to be 4 root 2. And that right there is our answer. And of course, we can plug it into our calculator and get a decimal approximation for whatever it is. But you know me, I don't particularly like decimal approximations. I prefer that. But if it's a multiple choice question on the AP exam and all they give you is decimal answers, then by all means plug it into your calculator and get a decimal answer to figure out which one they're leading you to. Now, those were kind of training wheel questions. Let's go ahead and do a couple that are a little bit more robust, lest, we walk out of here disappointed. So, 0 to 3 of 2 sine x minus e to the x dx. Now, that shouldn't be too difficult, and remember that you can actually pull this apart if you wanted to. You could actually pull this apart into this integral and pull it apart into that integral. Now, I'm not sure that this is particularly helpful, largely because then you have basically two sums. You have this f of b minus f of a, and this f of b minus f of a. Okay, so you have a difference minus a difference. I would rather just keep it all together, whatever your fancy is. It really doesn't matter to me. Determine which way you're going to make the fewest careless errors and do it that way. I'm going to go ahead and do it from here. Now, what is the antiderivative of sine? Now, I know that the derivative of cosine is negative sine. So negative cosine's derivative must be positive sine. And therefore, when I antidifferentiate this, I'm going to get 2 cosine x. And when I differentiate e to the x, its derivative is just e to the x. So when you go the other way, there will also be just e to the x. Now, I have done my antidifferentiation. So the integral sign goes away, as does the differential right here. And I still need to plug in. So basically what I get here is I'm going to get negative 2 cosine of 3. That looks a little bit odd because we're used to having, pi values in for cosine, but that's still a legitimate value, and it actually will spit out a decimal approximation when plugged into your calculator. And then e cubed. Then, and you're like, oh, well, plugging in 0 is just going to be 0, right? Well, not true, because cosine of 0 is 1, and e to the 0 is 1. And so what I have here is I have negative 2 times 1 times cosine of 0. I guess we can just put that in there for right now, minus e to the 0. Now this negative right here is bugging me, so I can go ahead and distribute it and turn both of those positive. And basically what I'm going to get here is this is 2 plus 1, so this is 3. And what I get is 3 minus 2 cosine 3 minus e cubed. And that right there, whatever the decimal approximation is for that bad boy, is going to be your answer. Okay. Now, we've done a couple of problems, and we could do a couple of more, but of course there are those other videos on Virtual Fourth that you can take a look at as well. You also have the homework and the solutions that I will post for you. So between this video, the old videos, the homework that you've already done, and the answer key that's posted, I'm hoping that we can hit the ground running on Tuesday and move pretty quickly on to the second part of the fundamental theorem of calculus, but I will save that for then. I'll see you on Tuesday, guys. Bye-bye.